In example 21.2, it says to solve each equation by expressing the exact solution in terms of natural logarithms, then use a calculator to obtain a decimal approximation for the solution. Now what we're looking at here in example 21.2 is a set of equations that the one-to-one property is not going to be applicable for. And the reason why the one-to-one property doesn't always apply is because the numbers don't always have nice power representations with the bases that are available. So for example, with part A, we have 10 raised to the x equals 8.07. If I want to think about taking 8.07 and somehow raising it, or having 10 raised to the something equal that for the one-to-one property to work, I'm going to have a really difficult time doing that with whole numbers. 10 to the first is 10, 10 to the second is going to be 100, and I'm looking to get 8.07. So maybe I should back up and go 10 to the 0, but 10 to the 0 is going to be 1. So that leaves the question, what does the exponent need to be in order to be able to get an answer of 8.07? And this is exactly why the logarithm is created. The logarithm makes it possible for us to be able to find the exact solution and then with our calculator come up with a decimal approximation, because we're not going to get a nice whole number answer. It's going to be a decimal. So that's kind of the motivation here behind this, well, why we're interested in the logarithm in the first place. So using the definition for the log, I'm just going to rewrite the statement in log form. Log, the base is 10, the argument will be 8.07, and this will be equal to the exponent, which is x. Now with this log, it's a base 10 log, so that's a common log. I can just write this as log of 8.07, and that should be able to be directly typed into your calculator. And I have 3 decimal places of accuracy already prepared. 0.907 is what we should get for that. So what we have here is both answers all written together on one line. The 0.097 is your decimal approximation, and the log of 8.07, this is known as the exact answer. So once you have an exact answer, then anybody could take that, plug it into a calculator, and get the degree of accuracy that they desire, whatever the decimal places are. So exact answers are useful, and they are good to have for that very reason. Let's look at part B. We have 9 times e to the x is equal to 107. Now we're going to run into the same issue that we did with part A, in that it's going to be difficult, if not impossible, to be able to rewrite 107 using a base of e. So e to the what would give you 107. Not only that, but there's another concern here. The other concern is going to be that this is not exactly the right format for us to convert from exponent form to log form. Here's what I mean. The definition says if y equals log base b of x, then we can convert that to b to the y equals x and vice versa. So the implication here with this definition is that there is an implied multiplier of 1. There's an implied coefficient of 1 with that exponential statement b to the y. That would be the 9 that we have here. 9 times e raised to the x. So this is not set up exactly for using the definition yet, but we can get there if we were to divide both sides of this equation by 9. So then I would end up with the statement e to the x equals 107 divided by 9, in which case e is treated as the base, x is treated as the exponent, and then the entire 107 over 9, which can be thought of as just a single rational number, that represents now the argument for the logarithm. So we'll convert this to log, base e, The argument will be 107 divided by 9, and this is going to be equal to x. We saw that log base e is the same as ln, so we would call this ln of 107 divided by 9, and that's the exact answer. We can type that ln statement directly into the calculator, and that would give us approximately 2.476. I'll box that in as both the exact and the approximate answers.